Welcome to another R tutorial. I'm Nate Fossey. Today we're going to talk about and examine graphically numerical data. Here you can see actually in the window the RStudio interface. Here's the accompanying PDF that will outline what we're going to discuss. We're going to talk about 5 ways to graph a numerical variable, and we're really talking about one variable. You can read those descriptions, but I want to emphasize this. All of these functions, all of these types of graphs, so the graphs are labeled in bold. The functions that we are going to employ from the Mosaic package are after the colon, and that's the syntax side. All of these are to reveal, are intended to display the distribution of a quantitative or numerical variable. I'm often saying quantitative, and it's really because it's a misnomer, because we can actually quantify, as we've done with the Titanic data sets, categorical variables. It's actually, in some ways, a holdover. In the 70s, categorical variables were sometimes called qualitative variables because they measure different qualities, like how much you liked something, for instance. That's beside the point. The relevant point here is that when we think about numerical variables, we're looking at an underlying distribution, a probability distribution. And that's what I want us to emphasize here. I think a lot of people are sometimes maybe confused by the idea of what a histogram is because they're not sure what the y-axis means, or a density plot, for instance, because it seems quite hypothetical. But the point here, or even a box plot, which also is based on the interquartile range, which isn't always intuitive. But the point here is, when we look at the first 2 kinds of graphs in particular, I want us to pay attention to the area under the curve. That we're looking at where things lie relative to one another, not necessarily where values lie with respect to some gold standard. We just want to know where one value lies with respect to another. And that's because with a histogram, you can assess it in many different ways. It can be a frequency plot. It can be, in other words, the y-axis could be the frequency of counts, for instance. It's comparable to a bar chart, really. More often than not, it's actually a measure of density or relative frequency. And this relative frequency is important. It's about the relative density of values within the distribution. And that's what the density plot is as well. The histogram is a little bit more, you could say, granular. You can specify the number of bins. What the density plot does is it estimates the underlying probability, the underlying distribution of the data, whether or not that's actually legitimate. As we'll see, we're going to look at age, and you'll see some oddities there. Of course, age is a continuous measure. I mean, everyone's aging by days, by minutes, and things like that. But that's not necessarily captured in the data set that we have, which is, we're going to look again at the survey of children in schools. But I just want to emphasize that it's about relative frequency, relative distribution. We want to look at the overall shape. You can almost squint your eyes and just see where do things lie. This is what you want to look at here. Same with the box plot. What the box plot adds, or what is also called the box and whiskers plot, quite colorfully, because you'll see that it has a little box here and the little whiskers. And you want to look for little dots that are outside of that. And those are typically cases that are defined as outliers in common parlance. The technicalities of that are covered elsewhere. in the lectures, or in statistical lectures. But the emphasis here again is on the distribution, along with identification of values that seem a little bit extreme. And those are worth examining, maybe not throwing out, but maybe examining whether or not those are faulty data or whether they are just simply cases that are actually naturally occurring. So those are informative. The last two kinds of distribution plots, and again, I'm calling these distribution plots, are for smaller samples. This is called the stem and leaf plot, which is quite useful, but you have to have a smaller sample. So we're going to use the sample function that we had used earlier to create a smaller sample of 20 odd, a score of students, and look at a score of students. And then we're going to look at the dot plot, which is each individual student plotted in relative to one another. So the latter two are for either subgroups, maybe you're interested in a subsample. So there's no data set that's really too small to examine, actually. You know, we're in an era of big data, but sometimes we may be interested in only very few important cases, because in some aspects of social science research, there are a few people or a few cases that are extremely informative. People with rare illnesses, for instance. Maybe people with living under extreme conditions. Maybe extremely influential people. If you want to look at, say, the population of living presidents, well, you're not going to have a lot of presidents of the United States. You're not going to have a large sample there, but you still might have information there. So what you do in statistics is you first kind of evaluate what you can do with the data at hand. And you can still do something with data. And that's what these latter two, the stem and leaf plot and the dot plot, are really useful for with numerical data, is looking at smaller data sets or looking at subsamples, for example, that are important to a theory or a question that you might have. And I have to say, some of the most cited medical research has very small sample sizes. I believe the most cited JAMA article has 18 people who have used some sort of respiratory device, and they're measured at 2 occasions. So technically, I think it has 32 data points, but it's only 18 participants. Tens of thousands of citations, I think. I will double check that, but we don't have to have a gigantic sample. So after that disquisition, I wanted to elaborate on that because I think this can be somewhat confusing for some people, especially when we're used to, say, counts or pie charts. So here we are, back to our script, back to our popular kids data set, and we have just finished our tutorial looking at numerical summaries of data. And quite often people just want the numbers. But I want to emphasize that statistics isn't always about the numbers, and in fact some of the best statisticians and scientists realize that there's something probably innate to humans that we can understand visual cues better. It's hard to see a distribution in a set of numbers, but it's quite easy. It'll pop out if you see it in a graph. So let's start with a histogram. We're going to look at age. And what I want to show with the histogram syntax here is, in this data set of children, well, actually, before we do that, why don't we just do our statistics on the age first, just so we can compare what it looks like to have a numerical summary with a graphical summary. So here's our favstats function. It's the same session as I had earlier. I kept it open, so I didn't have to reinstall the Mosaic package. I just wanted to explain that. But what do we have here if we highlight age? We see, well, the youngest child in this sample is 7. The oldest is 13. The kids are on average about 10.5 years old, and they average about a year. They vary about a year, or the standard deviation. The median, they're split right around age 11. Okay, so you got a few that are quite young, but most around, 10, 11. Oh, what we have? Yeah, 10 or 11, right? That's the interquartile range right there. So let's take a look at what this distribution of age looks like graphically. We're going to do a histogram, and what we're doing here is we have the tilde here as we have with our Mosaic commands, functions rather. I'll sometimes use the word command. That's common in more typical stats packages, as you would, but in R we like to call them functions. We specify the data set, we have that argument, or data frame. Here we have the number of intervals or bins, and this is important in representing a histogram, and it actually can substantially alter what a histogram would look like. So I'm just going to press Control Enter here, and we should have the graph here. Let's see, why is that not showing? There we go. Okay, so that took a little while to load up. Well, that is not very informative, is it? Because as we saw from the data sets, okay, we got very few kids in the 7 group. So let's increase the number of bins, and maybe we'll get something a little bit better. I just saved the syntax. I'm going to run it again. That's a little bit better. That gives us an idea of the range, the distribution here. Maybe not as informative as we would like, especially given, let's see what we have. We have an interquartile range of 10, 11, 12. We could probably, well, let's add, I don't know. Let's add 6. Do we have 6? We have 7 die. Let's add. Well, we won't have 8. We'll have 13, 12, 11, 10, 9, 8, 7. So we'll have 7 possible values, unless I got that wrong. 13, 12, 11, 10, 9, 8, 7. Got it right. 7, 8, 9, 10, 11, 12, 13, 7. There you go. Okay. Third time is a charm. You always got to triple check that. Okay. So look at, this is an interesting distribution. I basically called it by the integers. That kid who's 7 years old seems to be an outlier, or kids, and we can actually specify that because we're going to look at the box and whiskers plot next. But before we do that, we're going to look at the underlying distribution. What I want to show to you and emphasize here is we can understand what age is. This is intuitive. What is density here? Well, this is something that adds to 1. And again, what we're looking at is the relative frequency here. So we have 0.4 plus 0.3 plus 0.7, that's 0.2, that's 0.789. That's about 100% there. So the point is that not that this has any intrinsic value, but that it has a relative value that gives us an idea of what the shape of the data look like. And that's crucial here. So we can represent this in terms of frequencies, which is common in histograms, but the histogram is about relative frequency. It's about the density. And we're going to see this in a little bit in a better way by treating this as a continuous underlying function. And you're going to see some issues here. But what do we see here? Well, we see peaks and valleys. Well, is it the case that children in the United States are not 9.5, for instance, or they're not 10.5? No, that's not the case. In fact, this is you'll see these little dots here. This is actually reflects the fact that this is the way the data were measured. So we don't have a continuous measure of age. We don't have measurements that are smaller than years. Well, although this is quite common to have measurements in terms of months or even, your birth date, and you can be very particular about age. But the point is, R is trying really hard to estimate the underlying continuous distribution. We know there is a continuous density distribution, and this is useful. It adds information, but perhaps not in all cases. So here we see, in some ways, how some careful thinking and examination of the data is relevant, because we can misrepresent the data. So let's go back. I'm going to use the back arrow to toggle back to our first histogram that only included 3 bins. Well, that's not very informative, right? All we're seeing is just a couple blocks here. And this is a little bit more informative. We could say this is probably even more informative. This might be a little bit too granular. It might be a little bit too detailed for this particular measure, simply because these troughs here, they certainly show the shape of the data, but they aren't necessarily I would say they would be misleading if you were just to show them to somebody. You might think, there's something that happened to these kids if you didn't, you want to be careful in the way that you represent these data, I would say. But you still see this little outlier here. So that 7-year-old, this is how a range is important. The numbers combined with graphics really give us an idea of what is going on. So let's go to this box plot. I call it a box plot. Some people call it a box and whiskers plot. And you'll see why. Right? You got the little whiskers here. Now this is an unusual box plot, but because if you recall what the box plot is trying to do, and you'll see this in this box right here, more often than not you'll see perhaps a line here bifurcating this box here. This is the interquartile range. But what is interesting here is the median is identical. It's hugging right on the edge of the interquartile range, which is exactly what we saw in the numerical summary. The median is equal to the 3rd quartile. 11 equals 11. So what does that say? Well, it essentially means that, well, I mean, in terms of the interquartile range, it suggests that the data are skewed somewhat to the left here. This little line here is, these whiskers here, by the way. So if we think about this as representing the difference between the 1st quartile and the 3rd quartile, that means you're taking 2 quartiles. That's 50% of the samples hugged within that range. And then what those whiskers are is those are dividing the remainder quartiles. So those are actually half of halves, I guess you could say. So what that says is there's very little out here outside of these whiskers. And by the way, there could be other ways to specify these dimensions, but the main point here is that we typically use box and whisker plots or box plots to identify these outliers and to look at the distribution in a little bit more detail. So here clearly we are confirmed that we have this number 7 here, and we also have a 13-year-old, or maybe a couple 13-year-olds. We can't, not really sure. There could be some overlap there that are skewing this distribution, and I think that's all what we should say here. And there's the fab stats there that we ran before, but I wanted to run it before we had that. So let's go to the last two. If we recall, I want to show this vis-a-vis the histogram. Well, the histogram you sort of see a little staircase going down. You see a little push to the left. Well, that's what you're seeing right here. Actually, you're seeing a little bit of a push to the left of that distribution, but the distribution is really hanging right around 11. Most of these kids are around 11, and that's what you see here and here, right? This is where the central tendency is. The spread is a little bit asymmetric on one side and another, and we have a couple outliers here. Okay, now we're gonna. So, what do we learn from this? Well, box plots are decent at looking at the outliers. Density plots are sometimes useful. Histograms depend on the number of bins, but the main point is statistics. The numbers should be evaluated in conjunction with many different angles. There are many different ways to look at the data. This is the best way to approach data analysis. Take a look at it from different angles. You want to see something. It's like if you're buying a car, you want to give it a test drive. You want to drive it on a gravel road. You want to drive it in different places. You want to really just see what the push the data and see where it takes you and what's going on with it. Now I'm going to show you two more distribution plots that are better for smaller sample sizes, simply because, and I have a little story about the stem and leaf plot. I was working with a policy professor, and I was looking at a very large data set, and I created these stem and leaf plots for this very large data set. And he asked me, why are you creating these stem and leaf plots? And I said, well, you can look at the output. You don't have to create graphs. And he said, well, and he said, okay, I'm just wondering because you're using up a lot of paper. And he was right about that. You get a good intuitive feel for the distribution, but it may not be as beneficial for extremely large data sets. And I'll show you why. But let's first go back to what we did before, which is we're going to take another random sample of these kids. Let's see if we have this. We don't have a Popular Kids 25 data set anymore, so we're going to do this again. We're going to define. Remember, we used the assignment operator. We're going to use this little sample function. So we take the sample, a random sample of 25 kids using our data set, and we're going to call it Popular Kids 25. This is very creative, I know. And there we are, 25 observations with 11 variables. First time I saw this, I think before it wasn't the first time, of course, I was just looking at this, and this is what I like about RStudio. It gives you lots of recommendations. It gives you an extra variable that gives you the original identifier, which is in the original data set, which of course it still maintains here, but if you want to change your data frame, your data sets, it gives you some sort of identifier so that you can later merge this, or in our lingo, melt it with another data, with your back to the original data set. It's just another way of keeping track of things. In essence, it's a key. So let's look at this little data set. We're going to do the head function. If you recall, these are the first few rows. I'm going to expand this. This is a problem I always have. You want to increase the size of the console when you have more variables. In fact, that's a limitation, I would say, of the head command. If you have a lot of variables, so-called high-dimensional data sets, if you have thousands of variables, this isn't going to be that useful. You have to actually subset the data first, and we're going to, that's later. That could be discussed later. But the emphasis here is, okay, here we have a data set. Okay, we look at these kids. Okay. What do we see here? Well, we see some values. We don't really know much about this. We're going to learn more if we're going to do a little stem and leaf plot. And here we're using the with function. So we're saying with this data set, and this is actually we should call these 25 kids. Oops. Although we could define it as 10, but we're going to do 25. Here we have the distribution of these 25 kids. Now, what is interesting here is that it includes, let's see if we can even count this. Here, I'm going to subset this to 10, actually. We're going to define our sample with 10, because this is an important point to examine when you look at a stem and leaf plot. It's actually even better with when you have fewer kids. Let's make sure I did that correctly. Okay, check this out. What's kind of cool here is you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 kids here. So it actually gives you an actual count here of and with the decimal points, which basically says if we had, say, more precise information like a 4.5, it'll break it down in that fashion as well. But since we have integers, these are just zeros. But those zeros themselves are kind of like a pseudo histogram. They give you kind of an idea of the distribution. So when we looked at that stem and leaf plot for the kids, with 25 kids, we'll look at that again. you'll see no, look, you see kind of almost a normal distribution. This would be like a histogram. And in fact, we could do a little histogram of this if we wanted to. I don't want to spend too much time on this, but I'm going to comment this out so you can sort of see this in one line here. So here's a dot plot, which is another way of representing a small data set. It's like a histogram, only you get to see the little data points. Okay, that's pretty rad. Here it is again. You see it with 5 bins. Now let's just see what happens if we do a dot plot with all the kids. I'm not even sure if this will. Okay, see, it just looks like a vertical line because you won't be able to see the individual data points. That's exactly what I thought. So in that sense, a dot plot is really not informative unless you have a smaller sample size. So with our 10 kids, for example, we can do look at that. We got very large dots, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? That's basically a different way of representing this little distribution here. Although, yeah. So that's all I think I want to emphasize here in terms of the dot plot and the stem and leaf plot. That they're ways of representing data, but that the stem and leaf plot and the dot plot are ways of representing individual cases for relatively small sample sizes. Probably fewer than 100. 100 would be the max. I want to show you one final thing. We're almost at about 30 minutes. I want to show you something that is important when we're using RStudio, because you might encounter this problem. We're going to try to create another histogram. We're going to create a dot plot with 12 kids. Notice I made that window quite small. Oh, here we'll just do we'll do 25 kids. Well, look at this. It still renders. Sometimes what you'll see, I've been trying to make this happen. With some plots, you'll actually see an error message if you actually make this area of the graph too small. Now, that doesn't seem to be the case here. It's pretty flexible. So here you are, and here we have some objects here. Now, let's say we're done with our analysis and we want to do something with this. Well, we got a bunch of data sets here. I'm going to end with one little command here in the last minute or so. And this is the remove function, which is we don't necessarily want to populate or leave our session with all of these objects here. Maybe we want to remove some of these. So let's remove that counts value. It looks like it's what is called a vector. Let's actually look at that. I'm going to use the print function, which actually just displays it within the console. Yeah. So that is the count, right? That's an accounts variable. So we're going to remove that. We don't need that. I'm going to clean up our little session, and then we can remove the other objects as well. Let's remove popular kids 25, and then we'll remove popular kids. And by the way, we can do this as well here. We can do this. Actually, I don't think we can necessarily. Let's see. Yeah. So I guess the problem with data frames is you can clean everything, but you can't necessarily remove each individual one, as you can with the plots. By the way, right? We can delete this plot, current plot. We can remove this one, but let's just clean the whole plot area, and then we'll remove that last data frame. So I altered some of the syntax here, but this is really the source syntax for the problem set. And I hope this has been helpful for visualizing and understanding the distribution of all of the numerical data that we encounter using a really fascinating data set that is worthy of further exploration and further examination. This is the 25 kids that we see here. So that's it for this session, and I hope you found this to be useful. Thank you very much.